Hello everyone, welcome to this presentation in which I'm going to show how to implement and create new components for LTspice. Okay, and for this we are going to use as an example a component which is going to be an operational amplifier. Okay, let's see first how we are going to model our operational amplifier. Okay, so our operational amplifier is going to be something like this. It will have two inputs, okay, the inverting input, the non-inverting input and the inverting input, and then the output, okay. For the model, we are going to consider an input resistance between both inverting and non-inverting input that we are going to designate as Ri. And for the output, we are going to consider a series resistance, Ro, and then a voltage source, okay, whose value here is going to be the differential gain times the differential voltage, okay, being the differential voltage, the voltage between these two inputs here, as we know. Also, we are going to model the frequency response of our operational amplifier following this typical response. If we represent here the gain of the differential, the value of the differential gain, it will be something like this. It will have a DC value that we are going to designate as AO, okay, and then a value for the cutoff frequency, F1, and we are going to consider that our operational amplifier is internally compensated, so that we are going to have a response that it has a constant slope until reaching the line of 0 dB, okay, here. And this will be a frequency which we are going to call the bandwidth frequency, okay. We are considering here that the slope here is constant and equal to minus 20 dB per decade, okay, as we know. Usually the parameters that we know when looking at the characteristics of the manufacturer are these two parameters, the DC gain and the bandwidth. Okay, typical values, for example, that we can consider, this will be 10 to 5, okay, which is 100 dB. Okay, and for the bandwidth, a typical value is around 1 megahertz. Okay, but these are going to be parameters in our component, so we are going to change them anytime. Okay. But in order to implement our model, we need to know this value of F1, okay, which is related to these other two. Okay, for this, we can obtain the expression of this line here, okay, which is quite easy to obtain. This line here goes through this point and this point, so we can express it like this: is 20 log of AO, which is the DC gain here, okay, the DC gain here at this level, minus 20 times log of the frequency divided by F1, okay, because here if F is equal to F1, then we have log of 1, which is 0, and then we have this value, and the other parameter for this line is that the slope is 20 decibels per decade, okay. So now we can apply this expression to this point here, and then we will obtain that the value must be 0 decibels, okay? Minus 20 log f BW divided by F1, and this must be equal to 0 dB. Okay, so solving this, which is very easy, we obtain that AO must be equal to F BW divided by F1. Okay, so F1, which is what we want to know, is equal to F BW divided by AO. Okay, this is the relationship between these three parameters. Okay, so now we can implement our operational amplifier in SPICE, but we are going to draw first the model. Okay, so our model is going to be something like this. We have the input resistance, okay, between the positive and the negative inputs. This is going to be node 1 and this node 2. And then in order to model this part, we are going to use a voltage source E1. Okay, E1 is going to be the voltage source that is going to model the relationship between the output voltage here, and the differential input voltage. Okay, but only considering the DC part of the response. So E1 is going to be defined like this. E1 is going to be the DC gain, AO, times the differential voltage, which in SPICE can be defined like this. Okay, the voltage between nodes 1 and node 2. Okay, but with this we will be implementing only a constant response, not dependent on the frequency. Okay, so now in order to implement this response, what we can do is to add here a series resistance and a parallel capacitance. Okay, say R1 and C1. Okay, so now the voltage here is going to be equal to the output voltage. Okay, sorry, it's going to be equal to the voltage at this point. Okay, say for example UX. Okay, and then in order to emulate the output resistance behavior, what we are going to do is to include another voltage source, E2, okay, with the series resistance, RO, and E2 is going to be equal to UX, okay, with the same frequency response, but now including the series resistance. So this will be the output 3. And this, we are going to consider this our node of reference. Okay. So the definition for E2 in SPICE will be like B of this node. So we need to have designators for all the nodes. So we can use, for example, letters. For this will be node 8, this will be node B, and this will be node C. So here we can say that E2 is going to be equal to the voltage at node B. Okay. So this will be our complete model for our operational amplifier, including the frequency response and a series resistance at the output. Okay, and also the resistance at the input impedance of our operational amplifier. Okay, now in order to implement in LTspice, we need to create two items, okay? The first item is the definition in SPICE of all the behavior of our operational amplifier. And the second one is the drawing of our components, okay? In order to save time, I have here both of them, and I'm going to explain you how to implement this. Okay, so here, in order to define our operational amplifier, we need to create a text file, which I have named as my opamp.sub, okay? Then we can start with comment, operational amplifier, and then in order to define our component, we start with this directive, subcircuit, the name of my component, my opamp, and then the names or designators of the pins, 1, 2, and 3, okay? Then we have defined a parameter, which is the number pi here that we need in order to implement our cutoff frequency. And then we start by resistance, the input resistance, which is Ri between nodes 1 and 2, okay? And the value, because the value of this resistance is going to be a parameter for our components, then we place this value between these brackets, okay, here. Then we define the voltage E1 between A and 0, which is the reference node, and the value is AO times the voltage between 1 and 2, okay? And then we need to do it like this, with this expression value equal and the expression again between these brackets, okay? And then resistance R1. For our resistance R1, we are going to select a value of 1, okay? And what is going to be the value of C1? Then we want that the cutoff frequency is going to be F1 here, okay? And is, as we know, in this circuit is equal to 1 over 2 pi times R1 and C1, okay? So this will be something like this. Then we can choose one of them, okay? For example, 2 pi and R1, we can fix it to 1, and then we have C1. And this, we want to be F1 equal to this value that we have calculated before. So is FBW divided by AO. So from here, we get that C1 has to be equal to 1 over 2 pi. When we can keep the 1 to know that we have here the value of the resistance, and then FBW divided by AO. Okay, so this is the value that we need to implement for our capacitance. Okay, so go back again here. So we have placed here resistance R1, okay, R1 between A and B, and the value is 1, okay, and then capacitor C1, which is between B and 0, okay, and then with this value 1 over 2 pi times 1 times FBW divided by AO, okay, which is the FBW is the value of the bandwidth, okay, and AO is the value of our DC gain, okay. So with this we can implement the required value of F1, and then we have E2, okay, E2, which is equal to BB, and then it is placed between node C and node 0, okay, value equal to BB, and then the output resistance RO between C and 3, okay, and its value is another parameter for our component, which is RO. Okay, and then we finish with ends and the name of our component, that in this case is my op-amp. Okay, and this is all. We can save and keep it. And now the other element that we need to create is the drawing for our component. And for doing this, we come back to LTspice and select File, New Symbol. Okay, we enter in this new screen here, and in this screen what we have to do is to draw the body of our component. Okay, then we need to assign to place the different pins of our component, and then to include the parameters for our component. Okay, so this is the 3 steps that we need to implement. So we go to edit, first we go to draw, and then with this we need to draw the body of our component. For example, for the operational amplifier will be something like this. Okay, and then we can draw the minus sign and the plus sign. Okay, for example, this one will be the minus. I'm going to locate it like here, and then to draw the plus, we can copy this and put it here. Okay, then copy again, rotate, and do something like this, and then go to now to edit and place the pins. Okay, add pin, for example, number 1 here, another pin, edit, pin 2 here, another pin 3 here, and so on. Okay, it is important that the label of the pins has to be equal to the label that we have used in our definitions. Okay, for example, here in our drawing we have used these pins 1, 2, 3 for the non-inverting input, inverting input, and output. Okay, they have to be the same in our drawing. Okay, also the same as we have defined here in our text file with the behavior of our component. Okay, so this is very important. Okay, and then in order to save time, I'm going to take the component that I have ready here. Sorry, I will go this way. And this is my opamp.asy, which is the complete component. Okay, and then we have here the pins, the body, drawing, and then we need to add in our component the parameters that are being used in our model. Okay, for doing this we go to edit, attributes, and edit attributes. Okay, and we enter in this window here, in which we need to include the following. The prefix is usually a X, okay, uppercase X, because it's usually the symbol that is used for sub-circuits. Then in this line, Spice model, we have to add the name of our model, which has to be the same name that we have used in this definition in our sub-circuit. Okay, here is my op-amp. Okay, then we have several lines for including different parameters. We have used here only the Spice line and the Spice line 2. In this first line, we write, okay, I equal to 10 E6, okay, so it's 10 mega ohms, and RO equal to 1 ohm. Okay, these are the values, the default values of the input and output resistances. And then we have here another spice line for the DC gain, which is 1E5, okay, which is equivalent to 100 dBs, and then the frequency corresponding to the bandwidth of 0 decibels, okay, which is 1E6. In this case is 1 megaohm. Okay, we can change this later if we want. And then this is a description, custom operational amplifier, and then we can write here anything that we want, and then here we need to include the name of the file that has the definition of our component. Okay, this is my opamp.sub, okay, which has to be the same as this file here, my opamp.sub, with all the definition that we have seen before. Okay. So this is basically what we have to do. Okay. We can decide if we want to make this visible, these parameters visible by default or not. And for doing this, we can go in here, edit, attributes, attribute window, okay, and then selecting here the different attributes, we can make them visible or not. For example, I can select value 1, say OK, and place value 1 anywhere I want. I can edit with right click this value, okay, and then select even the font size to 1.5, which is the default if I want, and so on. Same thing with the other, okay, and then they are going to be visible by default. Okay, we don't want this value right now, so I'm going to delete it, okay, and then just save, and we have ready our component. So now we have everything ready to test our component. Okay, we have the symbol and we have the description of our component. Now, in order to test this component, the first thing that we have to do is to copy the symbol and the definition of the component in the folders corresponding to the program. So for this, we have to go to documents. Let's say, for example, we copy the symbol first. Okay, copy, and then go to documents, LTspice, lib, sim, and copy here our component. Okay, we paste here our component. And then we go back, take the description of the operational amplifier, copy, and go to documents again, LTspice, libraries, and subcircuit. Okay, and we paste here the component. Okay, so now we have everything ready to start using our operational amplifier. For this, we go to LTspice, and then here we can draw a new circuit using our new component. So for this, we go to this button, press here, component, and if everything is okay, then we should find here our component, my opamp. Okay, select it and place it around here. For example, we can also rotate, or we can do a mirror. Okay, so we are going to place it like this. Okay, and we are going to implement an inverting amplifier. Okay, let's move, for example, these parameters to the bottom. Okay, and then we need two resistances. We are going to rotate like this and use another one here. Okay, and then do the wiring with this wire here. We are going to connect our component like this. Okay, this will be the output. This will be the input of our amplifier. This is going to be an inverting amplifier. So this is going to ground, and this is going to be the input of our amplifier. Okay, say that, for example, we are going to have a voltage gain of 10. Then we use here 10 kilo ohms, sorry, 10K, okay, and then here 1K. Okay, so the gain is going to be minus 10. Okay, then we are going to use labels for the out. Okay, and then for the in, we place this one and then edit it. So in, okay, and then we are going to insert a sinusoidal voltage here at the input. For this, we go again to component, then select the voltage source, voltage, okay, place the voltage around here, and then do the connections, ground and wiring. Okay, and then we are going to select here a sinusoidal voltage source, for example. So go to advanced, then select sine. Okay, DC offset, we are not going to use DC offset, so this is going to be 0. Amplitude, say for example 1 volts, and frequency 1 kilohertz. Okay, and the other parameters we can do as default. Okay, so we don't write anything here, and this is as simple as this. Okay, so now we can define our simulation. Go into simulate, edit simulation command, okay, and select a transient simulation. So we are going to see this is a frequency of 1 kilohertz, so it's 1 millisecond period. We are going to see, for example, 3 periods, okay, 3 milliseconds. And in principle, we don't need to include anything else. We can leave the rest as default. So we have here our directive for this simulation, okay? So right now, we only have to run and see if everything is okay. Okay, so we have one problem here. So is this that trouble writing this document? Okay, so we need, sorry, to save our document in a place that we can write, for example, say in downloads, and say our test op amp. Okay. So I think that now everything is okay, so we can run, and this will be the results. Okay, so here we have our circuit. I can go to the input and see the input that we are injecting in our circuit, okay, with an amplitude of 1 volts. And if I want to see the output, then I can see the output, which is a sinusoidal waveform, okay, 180-degree lagging the input voltage, okay, and with an amplitude of 10 volts as expected, okay, so everything looks good, okay. Now we can obtain also the frequency response of our amplifier, and for doing this we need to inject an AC signal here at the input. Okay, so we can edit this voltage source by right-clicking on it, and then we have here this parameter here, which is the small signal AC analysis information. So we can include here an AC amplitude of 1 volt, for example, 1 volt, and then here the AC phase we can leave this as default, which will be 0 phase initially. So we select OK. So we are now injecting here an AC small signal voltage of 1 volt. Okay, so we can go back to our original gain of 10, which is easy to understand, and then we need to define our AC analysis. For this, we go here to simulate, edit simulation command, and then we select AC analysis. Okay, AC analysis. So here we have the different parameters to define our small signal AC analysis. Okay, so we select the type of sweep. We have different possibilities. We are going to select the decade. Okay, then the number of points per decade, say for example 100. The start frequency 1 Hz, and the stop frequency we are going to stop, for example, at 10 megahertz. We can do it like this, 10E6. Okay, and then place this directive here, for example, and you know that automatically LTspice makes this other directive a comment. Okay, so we are going now, when we run our simulation, we are going to perform the AC analysis only. Okay, so now we can go and run and see what happens. Okay, so we can see here the output voltage. We can remove this one and see the output, which is already in dBs. Okay, so we can see that the DC gain is 20 dBs. Okay, corresponding to a gain of 10. Okay, 10K over 1K. Okay, and then this line, this continuous line, corresponds to the phase of our amplifier. Okay, so if we want to, for example, calculate the cutoff frequency, we can select the cursor here, first cursor, for example. Okay, and then because here we have 20 dBs, we know that the cutoff frequency is at the point in which we have 3 dBs less than the DC gain. Okay, so it will be 17 degrees. So we select here until we get more or less to 17 dBs. Okay, so this will be our cutoff frequency in this situation, which is 90.3 kilohertz. Okay, for example, another analysis that we can do is if we remove this resistance here, we can do this, remove this resistance, then the response that we are going to get is the same response as our operational amplifier that we have seen before. Is like this. Okay, is the DC gain with frequency F1, cutoff frequency F1, and reaching 0 dBs at the bandwidth frequency, okay, which is 1 megahertz. So let's try this. Okay, run, and then we can see now that the DC gain is 100 dBs. Okay, and the cutoff frequency would be at the point in which we get 97 dBs. Okay, so now it's 97.02 dBs, and the cutoff frequency is 9.9 Hertz. Okay, which is in agreement with our design for the operational amplifier. Okay, so with this, we finish this presentation. I hope that this has been useful for you, and we can meet again in another video. Okay, thank you very much and goodbye.